In this video, we're going to look at the scale of black holes in the universe, but we're going to do it in a way that's a little unusual. To do these things justice. First, we need something big to compare them with. So let's use our solar system. We're going to make a scale model of our solar system somewhere where we can get a good sense of that scale, like here in Manhattan, New York. The first thing we need for our scale model is Earth. And we're going to make it the size of a grape here. If the Earth is a grape, the Sun is the size of a large elephant. It's pretty huge, but this is a little too close. We need to put it 400 meters or 4 football pitches away. Let's add in the other planets of our solar system here in New York. There's giant Jupiter there. It's about the size of a beach ball. The last major planet is Neptune. It's out beyond the Statue of Liberty, 11 kilometers away from the Sun. It's about the size of a melon. You can see why it's difficult to see Neptune. We're on a grape trying to look at a melon in the dark, almost 11 kilometers away. But now that we've got our scale sorted out, how big is the smallest naturally occurring black hole compared with the solar system? Well, it would be... Actually, it would be just this big. Smaller than a fine grain of sand. Black holes are tiny. It's obviously much smaller than the Earth. It's about the same size as the asteroid that wiped out the dinosaurs, which is also surprisingly small. Black holes can be smaller than asteroids. Isn't that crazy? Now you might think, well, that's a special tiny black hole that doesn't have much in it, but it's not. That grain of sand started out as this, an O-type star, 10 times wider than the Sun and 35 times the mass, the size of a large hot air balloon on our Earth grape scale. When a huge star like this reaches the end of its life, it explodes as a supernova. I've sped it up here a lot. Most of the star bursts outwards, forming a huge cloud of gas and dust, thousands of times bigger than our solar system. But it leaves behind a core of iron and nickel, a little smaller than our Sun, but with more than 2 times the mass. And the iron and nickel atoms just aren't strong enough to resist the crush of their own gravity. It collapses, and atoms are so empty they almost seem to disappear when they're crushed. They are crunched down to a clump of neutrons called a neutron star. It's so dense you can see it bend light around it. If it's as heavy as 2.2 suns or more, as it is in this case, even the neutrons aren't strong enough to fight their own gravity. So it collapses one more time to form a black hole. The mass of more than 2 suns is now inside a black sphere just 13 kilometers across, smaller than a fine grain of sand on this Earth grape scale. But black holes aren't quite what they seem. Now, just to get close up with a black hole for a second, a black hole is 2 things. There is something in the middle called a singularity, and a black sphere around it called the event horizon. Let's chop it in half for a moment. Basically, inside the black hole, the singularity is the crushed core of the star. The exact size of the singularity is still a bit of a mystery, because it breaks our current theories of the universe. It may have no dimensions, just a dot. Or it may just be incredibly small. We can describe the world outside the event horizon very precisely, but for now at least, the singularity requires improvements to our understanding of physics to fully define. It doesn't help that we will never see it. This is because this crushed star has so much mass that it reaches out with its gravity and pulls everything nearby in, including light, creating this black sphere around it, the event horizon. It's a cloak of blackness that we think is probably just empty. It just marks the point of absolutely no return for anything. But you're not simply safe outside it. Small black holes in particular have something called a gravitational gradient. All that means is when you get close, you will inevitably be turned into spaghetti. Seriously, you are pulled much harder at the front of your body than at the back, and it will just stretch you out more and more the closer you get to it. It's called spaghettification. With really big black holes, that doesn't happen until you're inside the event horizon. But whether it's inside or outside, you can't avoid gravity when you get close to the singularity. You will inevitably be ripped to shreds very quickly. I often hear people say they'd like to fall into a black hole just to see what's inside, but I wouldn't recommend it. If you're lucky and it's a huge black hole and you can avoid all the other matter falling in with you at incredible speeds, you'd pass the event horizon and you'd likely momentarily see only darkness in the direction of the singularity, not be able to tell anyone about it, and a fraction of a second later you'd be instantly turned into spaghetti. So this is the theoretically smallest black hole we can have, but the smallest we found is a little bigger and likely around 6.3 solar masses in weight. It's the size of a fine grain of sand. If you thought it was hard to find a melon-sized Neptune, imagine trying to see an absolutely black grain of sand in the blackness of space, way outside the solar system. We have to look for either its immense gravitational effect on things, its ability to bend light around it, or the incredibly intense light given off when things fall inside them. So why have I made this huge scale model of the solar system if black holes are the size of grains of sand? Well, it's because black holes don't just like eating spaghetti, they like eating stars too. So to understand the next bit, we need to talk about galaxies briefly. We live in a galaxy, the Milky Way, about